Hydrogen is the most efficient rocket fuel ever created. So why does NASA stop using it the moment it reaches space? That's the contradiction at the heart of the NASA's Artemis program, and once you see it, you can't unsee it. Because this isn't just about rockets. It's about how real energy systems behave under pressure, and why the most perfect technology often fails when the system changes. When the Space Launch System ignites, it represents one of the most extreme energy events ever engineered. The sky doesn't just light up, it fractures. Twin solid rocket boosters roar to life, while the core stage feeds 4 RS-25 engines with liquid hydrogen and liquid oxygen. Together they generate thrust so immense that it overcomes Earth's gravity and sends a spacecraft the size of a building into space. At that moment, hydrogen is king. It delivers unmatched efficiency, more energy per kilogram than any other chemical fuel we can realistically use. In the physics of launch, that matters more than anything else. Every kilogram saved compounds across the entire mission. Hydrogen doesn't just help, it defines what's possible. But here's where the story begins to shift. Because even as hydrogen dominates the most powerful phase of the mission, it is already creating problems inside the system. During multiple Artemis preparations, engineers have faced recurring hydrogen leaks, tiny, almost invisible failures that force massive delays. These are not dramatic explosions, they're quieter than that. Seals that don't quite hold, connections that don't behave under cryogenic conditions, molecules that are simply too small to contain. Hydrogen doesn't just power the rocket, it challenges it. And this is the first clue that hydrogen is not just a fuel, it's a systems problem. Because the moment the rocket leaves Earth, everything changes. Launch is about brute force, space is about precision. On Earth, you fight gravity, drag, and structural limits. In space, those forces disappear. Instead, you're navigating a vacuum where tiny changes in velocity determine whether you reach the moon, or drift endlessly into deep space. The rules are different, the constraints are different, and the fuel that dominated launch suddenly becomes less useful. This is where the transition happens. After separation, the Orion spacecraft relies on the European Service Module, developed by European Space Agency and built by Airbus. And here's the surprising part: it doesn't use hydrogen. Instead, it uses hypergolic propellants, monomethylhydrazine and mixed oxides of nitrogen. These fuels are, by almost every efficiency metric, inferior to hydrogen. They produce less thrust per unit mass, they are toxic, they are dangerous to handle. If you were designing a system purely for performance, you would never choose them. And yet NASA does. Because in space, performance is no longer the dominant constraint. Reliability is. Hypergolic fuels ignite on contact. No spark, no ignition system, no complex startup sequence. When you open the valve, they burn. Every time, instantly, predictably. They can sit in tanks for months without degrading. They don't require cryogenic storage. They don't boil off into space. They don't leak through microscopic imperfections at the same rate hydrogen does. They are simple. And in deep space, simplicity is survival. To understand why hydrogen disappears from the system, you have to look deeper into its physical nature. Hydrogen is the smallest molecule in the universe. That makes it incredibly light and incredibly difficult to contain. It slips through seals, it permeates metals. Over time, it escapes. But the bigger issue is temperature. To store hydrogen as a liquid, you must keep it at around -253 degrees Celsius. That requires advanced insulation, constant thermal management, and carefully engineered tanks. Even then, it slowly warms up, and when it warms up, it boils. This is called boil-off, and it is one of the most important constraints in hydrogen systems. Even in the vacuum of space, with no atmosphere to transfer heat in the traditional sense, thermal radiation slowly adds energy to the tank. The hydrogen warms, transitions into gas, and escapes. You are losing fuel simply by existing. In launch, this doesn't matter, the fuel is burned within minutes. But in space, time becomes the dominant variable. Missions last days, weeks, or months, and over that time, hydrogen disappears. So the most efficient fuel becomes unreliable. And in space, reliability beats efficiency every time. This is the core system trade-off inside Artemis. Hydrogen wins where energy density and performance matter most, during launch. Hypergolic fuels win where reliability and controllability matter most, in deep space. And the system doesn't try to force one solution across both phases, it adapts. But the evolution doesn't stop there, because propulsion is only one layer of the system. Once Orion is in space, it deploys 4 large solar arrays. These arrays generate electricity for everything on board: navigation systems, communications, thermal control, onboard computers. This is another transition that often goes unnoticed. Earlier missions like Apollo used fuel cells powered by hydrogen and oxygen to generate electricity. It was an elegant system, highly efficient, compact, and reliable for short missions. But Artemis moves away from that. Instead of consuming stored energy, it generates energy continuously from the sun. This is the shift from consumable systems to renewable systems. Fuel cells require reactants. Once you run out, you lose power. Solar arrays, on the other hand, provide energy as long as sunlight is available. For long-duration missions, they are more sustainable, more scalable, and less dependent on stored resources. So once again, hydrogen is replaced, not because it doesn't work, but because the system evolves. And this is where the story expands beyond space, because the same pattern is playing out right now on Earth. Hydrogen is often presented as the future of energy, a universal solution that can replace fossil fuels, power industries, and enable deep decarbonization. And in isolation, many of those claims are valid. Hydrogen is versatile. It can be produced from renewable electricity, it can store energy, it can decarbonize sectors that are otherwise extremely difficult to clean. But when you place hydrogen into real-world systems, the same constraints appear. Storage becomes difficult, infrastructure becomes expensive. Energy losses accumulate across the value chain, from electrolysis to compression to transport to end use. Reliability becomes harder to guarantee. Utilization rates become critical for economic viability. And suddenly hydrogen is no longer the obvious answer. It becomes one part of a larger system. This is exactly what Artemis reveals. It doesn't treat hydrogen as a universal solution. It uses hydrogen where it performs best and abandons it where it doesn't. It combines multiple energy systems into a layered architecture, each optimized for a specific phase of the mission. At launch, hydrogen dominates because efficiency under extreme thrust conditions matters. In space, hypergolic fuels dominate because reliability and simplicity matter more than efficiency. For onboard power, solar dominates because sustainability and longevity matter. Each phase selects a different solution, not because one is better, but because each solves a different constraint. This is systems thinking, and it is the missing piece in most discussions about hydrogen today. Because the real question is not whether hydrogen is efficient. The real question is whether hydrogen can survive the system it operates in. If storage losses are too high, the system fails. If infrastructure costs are too high, the system fails. If utilization is too low, the system fails. If reliability is not guaranteed, the system fails. This is the same test every space mission must pass. And it's the same test every hydrogen project on Earth must now face. If subsidies disappear, does the project still work? If demand fluctuates, does the system remain viable? If integration with existing infrastructure is incomplete, does the model still hold? These are not technology questions, they are system questions. And Artemis answers them in a way that is both simple and profound. It does not force hydrogen to work everywhere, it designs a system where hydrogen works somewhere. And that is the difference between a technology that looks good on paper and a system that works in reality. If you want to go deeper into how hydrogen actually fits into real-world systems, from cost structures to infrastructure constraints to project execution, that's exactly what we break down inside H2 Hub by Renee Energy. Because understanding hydrogen is not about understanding the molecule. It's about understanding the system around it. Because in the end, the future of energy won't be decided by the best fuel. It will be decided by the systems that survive. And right now, Artemis is showing us exactly how that future is being built.